So today we're going to talk about this research paper, Distillation Scaling Laws, put out by Apple Inc. And this paper is very interesting overall. It's a long paper, 67 pages. So if you're interested in math and all of the statistics and the full breakdown, all of their experimentation as to how exactly they arrive at their conclusions, they give you 67 pages of it. And it's awesome. And it's a great breakdown, right? I mean, this paper is just, it's all math, right? Like the equations, like all of the experiments. So it's like, really deep analysis on that level. And then so if you are interested in like that super deep mathematical analysis, the research paper, I'll leave a link to the research paper itself. If you want an explanation of this, like a full-on, let's dive deep into the research paper, into every part of this 67 pages. I also have a podcast that AI has put together that I will leave a link to for the description for my second channel. That's like if you don't want to read the paper, if you'd rather go through that method. And then here today, what I'm going to do for you is essentially give you the full code breakdown and the overall explanation and implementation of this research paper and what it does. The big thing that this paper does is it introduces a singular scaling distillation law. This 67 pages is in support of, at the end of the day, one scaling law, which is why I'm setting it up this way, right? But I mean, it's a lot of analysis. And then so the paper introduces a distillation scaling law that predicts the performance of a distilled student model based on the compute resources allocated to both the student and the teacher. The law shows that the teacher's size and training data mainly determine the student's performance through the teacher's cross-entropy loss. And the teacher's cross-entropy loss is important. We're going to dive into all of that in this video. Like that's 90% of this video. And also highlights a capacity gap where an overly capable teacher can hinder the student's learning. The law reveals that supervised learning is more efficient if sufficient data or compute is available, or if a teacher needs to be trained solely for distilling one student. However, distillation becomes more efficient in the presence of an existing pre-trained teacher or when multiple students are distilled from the same teacher. Bottom line is like at the end of the day, you want the smartest teacher possible and you get the best results out of it. Go figure. And that scaling laws like don't necessarily apply here, right? That they kind of it's across the board within that, and like there's not a one size fits all equation within this, which is like backs up a lot of AI overall, right? Everyone wants like these silver bullet things like, okay, this is the one answer, this is the one thing, or this is the one thing that's going to drive us forward, or we have now, found this one thing that's going to move us from A to Z. And it's not like that, right? This is, oh, this is cool. And then so this is information that we found that's like H, and then potentially it gives us meaning when we come across M at some point or N. Like, and it's kind of, it operates in that capacity, right? And like other thing, before I dive specifically into this, I do want to highlight, like, it's apparent to me reading through these Apple research papers, the Apple researchers aren't, in my opinion, a fan of the Transformers architecture, just highlighting it, and it shows within the research and the experimentation that they're doing, right? Like, my assumption is that they wouldn't be doing these experiments in the first place and putting out this research and these laws, which I'm very thankful for, and that's why I'm making the video for. Thank you for doing the research. It's just like, my opinion is, and my assumption within reading these papers is that they're not huge fans of the current architecture, and then that would also be in alignment with Apple isn't releasing a lot of actual models, right? They're releasing a lot of papers like this, which is great, but I think that they're in the same boat as me within this, and then so just highlighting that and pointing that out. And then so diving specifically, let's dive, first of all, I want to dive into the general concept of cross-entropy loss, and then I want to dive specifically into how this Apple research paper gives a method at the end of the day for measuring and calculating this cross-entropy loss between student-teacher models. So you can utilize this equation and you'll know up front, like if your student model is going to be good based off of the equation that they put out from this research paper, which is why it's so good, right? But it all boils down to this function of cross-entropy loss. So let's understand that first. So, cross-entropy loss is like comparing answer sheets. Imagine you're grading a multiple choice test. Cross-entropy loss is a way to measure how well a machine learning's models answers its predictions. It matches the answer key, so like the true labels. It's particularly good for tasks where the model has to choose one answer from a set of possibilities, like classifying images or predicting the next word in a sentence. The basic idea is very straightforward. The model's job is to essentially guess the correct answer for each question. Instead of just picking one answer, it gives a probability for each possible answer. For example, if it's trying to classify a picture, it might say, I'm 80% sure it's a dog, 15% sure it's a cat, and 5% sure it's a bird. And then the true answer, the ground truth. This is the correct answer. We represent this as a perfect probability distribution. If the picture is actually a dog, the true answer is 100% dog, 0% cat, 0% bird. Cross-entropy loss, measuring the difference. Cross-entropy loss measures how different the model's probability guess is from the perfect true answer. Lower loss means the model's guess is closer to the truth. And then so in this instance, if it's 80% sure it's dog, then it's got a cross-entropy loss of 0.20, like 0.20 plus, like, we'll, use equations for that 15% cat and 5% bird. So let's say it's like 0.252 or 0.25250, right? And then that would be high cross-entropy loss because it's not like we want it to be more confident that it would be dog, right? So we would say that's a bad cross-entropy loss in this instance. And then so the formula, you can break it down to a mathematical equation that is not very simple, but it breaks down very simplistically into code. So the full formula can look intimidating, but in code, it's a lot less intimidating, right? So essentially, loss equals your true answer choice for 1 times the model's probability for choice 1 plus the true answer for choice 2 times the model's probability for choice 2, and then you just keep adding and stacking onto that. So think of it like this. For each possible answer, we look at 2 things. 1, is this the correct answer? So the true answer equals 1, if yes, and then 0, no. So is it a 1 or a 0? How confident was the model in this answer? So going in between 1 and 0, right? If it was 80% confident, it's a 0.8. We take the logarithm of the model's probability, the log of the model probability, and the logarithm makes the penalty bigger when the model is very wrong. We multiply these things together. If it's the wrong answer, the true answer is 0, so the whole term becomes 0. We only really care about the correct answers. We add up these values for all of the possible answers, and then the negative sign at the beginning just ensures that the loss is a positive number because logarithms of probabilities between 0 and 1 are negative. So then we break this down into essentially binary classification, so yes, no, cat, dog, etc. And then this is a special case where if the true answer is 1, we only care about the model's probability, and then the second part becomes 0. And if the true answer is 0, we only care about the model's probability, and then the first part becomes 0. This is like saying how confident was the model that the answer was not 1. So breaking this down into a real-world example, taking it away from the abstract mathematical terms, is it a dog or not? Let's say our model is trying to decide if a picture is a dog, which would be 1, or not a dog, which would be 0. A good prediction, we want it to say 1, right? If the model guesses 90% sure, it would be a 0.9. And then so it would have a model loss of 0.1. Model's doing well, like 90% is good, right? So a bad prediction would be if it guesses, let's say that it's 10% sure it's a dog, and then we would jump that number. So a 90% would give you a 0.1 on the loss, whereas if it's giving 10%, the loss would be like 2.3, right? It's very significantly, 2.3 is very significantly higher than 0.1. And then so models penalized heavily for being wrong, right? And it's confident about its wrongness in this instance. And then so if the model's confident and right, then we have low loss. If the model's confident and wrong, we have high loss. If the model's unsure, we don't penalize it as much. And then essentially we can utilize language models for this. So imagine the model's trying to predict the next word in a sentence. It's like a huge multiple choice test where the choices are all of the words in the vocabulary. And the model gives a probability for each word being the next word. Cross-entropy loss measures how well the model's predicted probabilities match the actual next word. And the formula is essentially the same as the many choices case, but we sum over all of the words in the sentence that we're training on. Why this works well. Essentially, it focuses on probabilities. It doesn't just care if the model picked the right answer. It cares how confident the model was in its answers. So it's rightness plus confidence, right? And then two levers. Two levers better than one. Smooth learning. The loss function is smooth and continuous, which makes it easy for the model to learn gradually. And it introduces strong penalties. So again, heavier and big penalties when it's wrong. In a nutshell, cross-entropy loss is like a sophisticated way to grade a multiple choice test where the model gives probabilities instead of just picking one answer. It rewards the model for being both correct and confident in its correct answers, and it penalizes the model heavily for being confident but wrong. This makes it a very effective way to train machine learning models for classification and tasks. And then so if we want to train a model on cross-entropy loss, here's an example, or utilizing cross-entropy loss, here's an example, right? And then this is just essentially the math that we just went over, and it's all math, right? But you just essentially break the math down into a function, and you just plug it into your function, and you get your cross-entropy loss. And then so this is essentially what we just described is a cross-entropy loss as a whole. What the Apple paper introduces is this cross-entropy loss to the student, right? So student cross-entropy loss. And then what does that mean and what's the difference? Let's break that down. So remember, traditional cross-entropy loss is like grading a multiple choice test. It directly compares the model's answers or probabilities to the correct answers, the ground truth. We focused before on using that loss to train a single model. Let's call this model the teacher for now. So now we are introducing a student-teacher relationship. So this is going to change, right? So knowledge distillation is a student learns from the teacher. And knowledge distillation is a technique where we have two models. We have a teacher model, which is a large, powerful, well-trained model. We already have its cross-entropy loss. We know exactly what it is, and we know how well it performed on its tests. We've benchmarked it already. And then we have our student model, which is a smaller, less powerful model that we want to train. Let's say our teacher has 400 billion parameters. Our student model could be 1 billion parameters, could be 7 billion, could be 150 million, etc. We want it to predict its cross-entropy loss without actually training it yet. So with this function that the Apple paper introduces, we know all of the parameters of our teacher model, and then we know the size of our student model, and then we want to know, once we train this, are we going to get a good student model or a bad student model? And we want to know this without actually having to train it. That's where the beauty of this equation comes in, right? We can do that. So the idea is that the student model can learn from the teacher model, becoming more accurate than if it were trained only on the raw data. It's like a student learning from a teacher's expertise and not just from the textbook. So this is where that distillation law comes in, the Apple law, and it predicts the student grade. So the distillation scaling law is not calculating the student's loss by giving a test. Instead, it's trying to predict what the student's loss would be if we were to train it using knowledge distillation. It's like trying to guess a student's final grade before the semester even starts. Based on, and this is how it works, right? It utilizes these 6 criteria. 1, the teacher's grade. How well did the teacher do? A better teacher usually leads to a better student. This is directly used in the final calculation, and the student's loss is at least as good as the teacher's and potentially better. The student's size. How many parameters does the student model have? This is like the student's brain power or capacity to learn. A bigger student can usually learn more, and this is referred to in the calculation. 3, the amount of distillation data. How many examples or distillation tokens are we using to teach the student from the teacher? More examples generally lead to better learning, but it's also more expensive, right? 4, the teacher's difficulty. The teacher effect part captures how hard it was for the teacher. Higher LT ratio, teacher did worse, or a lower DS ratio, fewer training examples, makes the teacher's task harder, and the relative improvement that the student can make is larger. The teacher had to do a hard task, and the student can build significantly on the teacher's knowledge. Basically, if it's a hard task, you give it a lot of information, it's going to learn more. If it's a simple task, give it a lot of information, it's not going to learn as much. Pretty straightforward, right? 5, the student's ability. The student's ability part is calculated based on how many parameters the student can utilize and how much data the student can utilize. 6, hyperparameters. These are like the tuning knobs that control how much of each of the above factors matter. They're usually determined by experimenting on many different teacher incident models. They're like the settings that adjust the formula to fit real world observations. This is where all your like all of your mathematical experimentation comes in, right? Like, do you add like Fibonacci sequences? Like, how exactly do you build this out? Like, what's the best way to go about that? That's where the tuning comes in. We don't know yet, right? And then so key differences. Here's a summary of the crucial differences essentially between the two methods, between traditional cross entropy loss and distillation scaling law, the distillation scaling law. I'll leave this here just so that you can have it here in the notebook. And then so in simple terms, traditional cross entropy is essentially, here's a test, what's your score? This distillation scaling law is, given how good your teacher is, how big your brain is, and how much you study with the teacher, what score do we expect that you're going to get? And we're like future cogging, right? We're predicting based off of these elements, do you get into the university or not? Like, what's your grade? Like, we're giving you your grade up front. Like, we already know. So the scaling law is a shortcut. Instead of spending a lot of time and computing power to train many student models, we can use this formula to estimate which student model and how much distillation data will give the best results. This is incredibly powerful for exploring different model architectures and training setups efficiently. It's a tool for predicting performance and not measuring it specifically. And here's the tool, right? Here's all the code. I lay it out specifically as I give you from the research paper. And the code isn't a lot, right? Because it's just the mathematical equations. But you plug in your parameters, so your student and your teacher parameters, and then you get predicted cross entropy loss based off of your parameters. Pretty straightforward, right? And then so what I can tell you is based off of this base model here, like our predicted cross entropy loss, we would not want to train this model. I can tell you up front, without training this model now, it would be a waste of money to train this model and to do distillation based off of the parameters that I have here in this default, you would waste your money. And now you don't have to. So you don't have to perform the experiment because we can predict with really good accuracy how it's going to come out. It's going to come out pretty bad. So I'll leave a link to this collab and as well as the paper itself. If you like this type of content, please like and subscribe. Thank you very much.